Arratsaldeon, muy buenas tardes. Con alegría, no exenta de emoción, presento al director de mi tesis doctoral en el Cavendish Laboratory de la Universidad de Cambridge, mi amigo John Pendry del Imperial College. Gizateriaren arauak, gizakiak erabilitako materialen izenen arabera izendatzen dira. Eta hori ez da kasualitatea. Har ditzagun esate baterako harri aroa, brontze aroa edo burdin aroa. Gaur egun nanomaterialen aroan gaudela esan genezake. Materialak neurrira ekoiztu ahal izango ditugu. John Pendry aro horren egiletako bat da, zalantza izpirik gabe. Berak asmautatako metamaterialak naturak eskaintzen duenaz haratago doaz, argiari iruzur egiten baitiote. Harry Potteren ikus ezintasunaren ametsa hurbilago omen dago. John Pendry combina de forma inusual y brillante intuición física y virtuosismo matemático. Su investigación de los efectos de campo cercano en electromagnetismo y metamateriales le sitúan en la cumbre de la creatividad. No muchos científicos pueden establecer un campo de investigación nuevo e inesperado. Este ha sido el gran logro de John en los últimos años en el campo de los metamateriales. Tiene una mente abierta, siempre abierta a nuevos retos, permanentemente preparado para saltar al siguiente tema de investigación. Es realmente extraordinario en producir nuevas ideas. Pero hay algo más. Como persona, es una persona leal. Leal con sus amigos. Nunca dice no a una petición de ayuda. Leal a sus colegas. Leal a su país y a su universidad. Y leal a la ciencia. Es el presidente del Comité Científico Asesor de Nanogune, que ha apropiado el título de Sir por sus servicios prestados a la ciencia y, consecuentemente, a la humanidad. Recibió la noticia en San Sebastián durante una estancia de un mes en el DIPC. No les oculto, lo pueden imaginar, que lo celebramos adecuadamente. John le dijo a su esposa Pat, antes de enviar a publicar su artículo sobre la lente perfecta: no sé, pero estoy convencido que si publico esto, o seré muy famoso en el buen sentido o tristemente famoso. Famoso ha resultado. John encarna el espíritu de Cajal al escribir que toda obra grande, tanto en arte como en ciencia, es fruto de una gran pasión al servicio de una gran idea. Con ustedes, Sir John Pendry.
Well, thank you, Pedro, for that gracious introduction. I only hope that I can live up to it today. Particular pleasure for me to be here talking to you tonight. I know San Sebastian well. I visited many times over the past decade and more, so it's also a great honor to speak to you tonight. I want to talk to you about light. Light is very fundamental to our lives because it's through light that we receive from the world most of the information that we have. And so it's natural that when man first came to study science, that it was a science of light that was one of the earliest to be investigated. So you might ask, after all these literally thousands of years, is there anything else to know, to find out about light? Do we know it all? And it turns out that we don't. There are still some things we need to find out about light. And recently, some of us have been looking into some quite exciting new developments. At any rate, we were very excited about them. Some of them were rather technical and involve differential equations and things. And we thought, are people going to get very excited with differential equations? Are you going to get very excited tonight? No, you're not, because I'm not going to show you any. So we thought of an alternative way of presenting our ideas. Instead, we asked, what can we do with these new ideas? And after a little thought, we thought, well, perhaps the most exciting thing we could do would be to hide something. And that's what my talk will be based around. But really, the cloak will be a vehicle for showing off these new tools which we have. So, first of all, a little bit of history of light. It's a very old history, so I'm not going to go right back to the beginning. But this man is very important. If you've ever had a physics lesson, you'll probably know about Snell and his law of refraction. Or if you happen to have a French physics lesson, it will be Descartes and his law of refraction. They thought of it about the same time, it turns out. And this law of how light behaves when it enters glass or water has been the basis of optical design for centuries and has served us well. But recently things have happened that means that Snell's law is no longer enough. We need a little bit more. Now, somebody else who contributed greatly to the science of optics is Galileo. He didn't invent the telescope, but what Galileo did was to make lenses much better than they were before, and using his very accurate lenses, he was able to see things that nobody had seen before, such as the moons of Jupiter, which he named after his patrons, the Medici. By the way, you may not know where the word lens comes from. It actually comes from this little bean, the lentil, and the lentil gave its name to the lens. Now, in the time of Galileo, people thought about light as a particle with, well, it may have had structure, but they certainly didn't know about it. But gradually it became apparent that light was much more than that. For example, it is now known that you can't focus light with an ordinary lens much better than the wavelength, and it's the internal structure of the light that prevents us from achieving that perfect focus. And so the next stage in understanding light came not on an experiment about light itself, but an experiment on magnetism, because the constituents of light are in fact magnetism and electricity. And this man, Michael Faraday, was a brilliant scientist, but he didn't work in terms of equations. He had very little formal education. He was a bookbinder, and he happened to go to the laboratories of the Royal Institution, where he was taken up by Humphrey Davy and made his assistant. And he went on to make some very important discoveries, and this was perhaps the most important discovery that he made. So here's a magnet, and this is a piece of paper over the magnet, and iron filings are scattered onto that paper, and the magnetic field arranges these iron filings, and so you can actually see the magnetic field revealed by these pieces of iron. And Faraday introduced a new concept into the way we think about forces. So two magnets either attract or repel one another depending on the sign of their poles. And the way people thought about it in the old days was action at a distance. So there were two magnets and they acted because of the distance between them. If you took away the second magnet, then nothing was happening. But Faraday said, well, that's not right. The magnet, whether or not there's a second magnet there, is surrounded by something which he called the field. So associated with the magnet is something which you can't see, until you reveal it with these iron filings, which is the field. And it's the field in Faraday's picture which exerts these forces. And that was a very important concept, this idea of a field. And he went on to show that if you move the field, for example, what he did was if you wrap a coil of wire around the magnet and then you move the magnet, then the magnet will induce a current in this wire, which he could measure. But it's only when the magnet's moving, it's a change in the lines of magnetic force in the field that induces the current. Now, Faraday was a great friend of James Clerk Maxwell. Maxwell was much younger, and he couldn't have been more different than Michael Faraday. Michael Faraday came from a poor background. He knew very little mathematics. James Clerk Maxwell was a rich Scottish laird, and he had lots of money, and he was very, very clever, especially at mathematics. And I promise you these are the only equations I'll show you, but I have to show you them because they're very famous. These are Maxwell's equations. And Maxwell took Faraday's ideas and he expressed them that the rate of change of the magnetic field gives you an electric field. And this is Maxwell's way of saying that. But he also realized that the theory was incomplete, that there's a symmetry between electricity and magnetism, and what one thing does, the other thing must do. And so he came to say, well, here Faraday says that if you change the magnetic field, you get an electric field. And Maxwell realized the complementary part of that if you change the electric field, you get a magnetic field. And it turns out that this was the key to light, because light is a dance. It's a dance between a changing electric field which creates a magnetic field which changes to produce an electric field. And the steps of the dance are the wavelength of light, and the beat of the dance is the frequency of the light. And it's this interchange between electric and magnetic fields that makes the light. And it's this internal structure of the light that prevents us doing a lot of things we want to do, which is a great challenge which I and my friends faced to control light at a level beyond Snell's law. Now, another man who picked up the theme of light was Albert Einstein, because Faraday had said that if you have a magnet, fields exist in space independently of whether there's another magnet to sense them. They're already there. And when Maxwell showed that light was a wave consisting of electric and magnetic fields, was a great puzzle, because this wave could go through not only glass or water, it could also go through the vacuum. And before Maxwell's time, if you had a wave, it was always a wave in something. So if you listen to a sound, we know that that's a wave, but it's transmitted through a medium, which is air. And you can think of many other examples of waves, and nearly all of them are waves in something. Maxwell's waves were waves in nothing. They were waves in the vacuum. And people were terribly puzzled by this and tried to develop a theory that there was really something there. There was a medium, a luminiferous ether, it was called. Nobody could quite pin down what this thing was until this man came along. And what he said is, well, you may call it the vacuum, but in fact, it has a structure of its own. And what's more, you can change that structure. So Einstein showed that in his way of thinking about the vacuum, about space, that if you had a very strong gravitational field, the way gravity acts is not really action at a distance. It creates a field, and that field is a distortion of space itself. And so the planets orbit the sun, of course space is bent. Now, if you take that to its logical conclusion, there's remarkable prediction which frightened people at the time, and it was that if space itself is curved, then surely if light goes through a curved space, it should move in a curved path. And hardwired into our brains is the idea that light goes in a straight line. The only reason you can see the people around you is that your brain has a little computer in it which says, the light's going in a straight line, and therefore this person must be over there. And if you do anything to violate that law, then your brain is very confused. And people were certainly very confused by this prediction of Einstein's. But in 1919, Arthur Stanley Eddington mounted an experiment to test this. And the experiment was that if you look at a star which vanishes behind the sun, and normally you can't do that because the sun's too bright, but if you choose the moment when there is a solar eclipse, so that the sun's light is blocked out by the moon, then the starlight should be deviated so it actually appears in a different place in the heavens from what it would be if the sun wasn't there. And the confirmation of Einstein's theory in 1919 was what propelled Einstein from being merely a very great and famous scientist to being the icon of science in the 20th century. In fact, what Einstein showed was when he put his theory into Maxwell's equations, he expressed the squashing of space by gravity in terms of something called the metric. And it's a very simple quantity. It just measures how much you've squashed space. And if you ask, where does this metric come in all this jumble of theory and so on, it turns out that it sits in exactly the same place as the refractive index. So what Einstein was saying is that the sun isn't just surrounded by a flat vacuum, it's actually surrounded by a slightly higher refractive index, and therefore it's behaving just like a lens. And gravitational lensing is one of the phenomena which are used in astrophysics these days to weigh galaxies and so on. So finally, after that series of history lessons, let me come to what we want to do. So here's the old optics, which has served us so well over the years. It makes this approximation that light is a ray. It doesn't take any account of this internal electric and magnetic structure. Mainly it works in terms of discrete refraction at interfaces. If you're designing a camera, what you're designing is really the shape of the surfaces of the lens. And it works in terms of a very limited set of material properties. In our new vision, what we want to do is to go beyond the ray approximation. We want to be able to control what's called the near field. That is to say, we want to look inside the wavelength and we want to ask what these component electric and magnetic fields are doing. And in doing so, we want to go into this region of sub-wavelength optics. We want to be able to beat this diffraction limit. We want to see things with light which are much smaller than the wavelength, which heretofore hasn't really been possible. And also, we want to do something which to exploit the potential of these things called metamaterials. Now, I'll come to what metamaterials are in a moment, but first, after this rather long introduction, let me get to what we all want to hear about, which is how we're going to make a cloak. And the idea is that we're going to make light, so like water. So imagine that we're a sort of super Einstein and that we can generate very powerful gravitational fields at will. So here's a beam of, too soon. Here's a beam of light, and this is going through ordinary space like we have in this room. And so it's going in a straight line. Now, you may not want it to do that. You may want it to go on a curved path. So you wheel up some black holes, quasars and things, and you make space really bent, and so light goes in this line here. Unfortunately, or perhaps rather fortunately, I can't show you a black hole and make a demonstration in a lecture theatre, but I don't need to, because we use this analogy which Einstein had between the squashing of real space and the effect of that on light, which is exactly the same as a refractive index change. So you can, from Einstein's equations, which relate the distortion of space to the distortion of the trajectory to the metric change, you can take over all of that theory and say, thank you, Einstein, I now know what the refractive index variation along this path is that's going to steer light in this direction. So, in principle, we have, through this theory which we borrowed from Einstein, we have perfect control over how light moves. And by the way, we have control not only of rays of light, but we've gone beyond the ray approximation, so we can actually control Faraday's field lines like this. So if this was a line of magnetic flux, the bending of space would change that in the same way. So, to make a cloak, well, to make something disappear, obviously that thing must not reflect light, otherwise you'd see it. So you might think that making something black would suffice, and indeed sometimes it does suffice. So if you're looking at a stealth plane, for example, it's covered with radar absorbing material, it doesn't reflect radar waves. And you can get away with that because usually in the sky the only source of radar waves is somebody who's trying to see you. But if we're in the world not of radar waves but of visible light, then there's light bouncing around all over the place. And for example, if you play the game of squash, you play it with a black ball. The black ball doesn't reflect any light, but the court is bright, painted white probably, and you can see the ball very well. Actually, you can't see it. What you see is its shadow. So the really hard thing about making something vanish is not simply to make it black, which I could do by taking a pot of black paint to this statue of Peter Pan. Peter Pan, you may remember, is a little boy who lost his shadow. And here is this statue, which is in Kensington Gardens, which is right next to Imperial College. So black is not enough. We have to find a way of getting rid of the shadow. And then Peter will be invisible. Now, how to do this? Well, here's a strategy. So here's something, a person or an object that you can see here, source of light, and you are looking at that object from this side of this structure. And your eye assumes that everything has gone in a straight line. So what I'm going to do, I say, okay, I'm not going to mess with these rays here. They have to continue in a straight line. Of course, if they don't, you know something funny is going on. But on the other hand, I can't let them go through this cloaked region here, and this region between the two spheres is the region I'm going to do the business of cloaking. So I'm going to design a structure that's going to send the rays of light around here, but it doesn't throw them away. It carefully keeps track of where they're going and returns them exactly to the same path here. And the way I'm going to do that in Einstein's distortion of space terms is I'm going to create this hidden space by putting my finger in space and tearing a hole in space, and all that space that was in the small sphere I'm going to squash into the annulus between the small sphere and the big sphere. And when I'm done, I'm going to say, well, Professor Einstein, please tell me, after all this destructive tearing of space I've done, what refractive index is in here, and Einstein's formula will then tell you the specifications for the cloak. Now, that's all very well, but usually we talk about refraction at interfaces. This is actually a continuous bending of the light, and we don't usually see that. Actually, occasionally we do, because it's exactly what happens in a mirage. So, I'm sure most of you know how a mirage works, but let me go through it anyway. So this is a classic mirage. It occurs in a hot desert. The surface of the desert is hot, and so is the air immediately above the surface. And that makes the air less dense and less refracting. So there's a gradient in refractive index as you move from hot air to cold air. And light from the sky, which if this hot air wasn't there would hit the ground, doesn't hit the ground. It's bent around by this gradient in the refractive index and reflected back, so that if you're standing here you can see the sky. And you think, that's funny. The only thing that does that is water reflecting. So your brain says, yeah, that's okay, that's water there, go drink it. Unfortunately, when you get there, it's just hot sand. In Northern Europe, we are more familiar with this road mirage. So sometimes on a very hot day, maybe every day in San Sebastian, I don't know, but in a very hot day in my country, the road will heat up and give this effect here. So the road looks as though it's wet. Usually in the far distance, when you get there, you see that it's really dry. So we're not going to use this old sort of refraction. We're going to use this continuous bending here. Now, so here's the scenario. And now it turns out that doing this continuous bending job is rather tricky. But fortunately, one of the new ideas we've had is a way of making completely new optical materials. These materials we call metamaterials. My Greek friends tell me that meta means beyond, so these are a sort of super materials. And let me explain what they are, because they're going to be very important to this story. Here's how an ordinary material works. If you send light through an ordinary material such as glass, the atoms and molecules respond to the electric field by polarizing a little bit. And the way light behaves is determined by an average over one wavelength cubed of light of all the molecules in that cubic wavelength. There are billions of them, so the average is very, very smooth, and the glass appears to be nice and homogeneous. If you want to change the properties of the glass, you change the chemistry. You put some lead in, make it more refracting, then you get table crystals, for example. Now, it turns out that the objects which are doing this response to the electric field do not have to be as small as atoms or molecules. They can be bigger structures. They can be a few nanometers across, a few tens of nanometers across in the case of light, and you still do this averaging business. And if there are a few tens of nanometers across, instead of doing chemistry, you can do engineering and make physical structures, which are still very small, but they're things that you can engineer rather than ask the chemist to make for you. And so the definition of a metamaterial is a material whose properties are derived from its physical structure rather than from its chemistry. And by the way, that physical structure must be much smaller than the wavelength, so the light doesn't see the individual units, but it does do an average over them. Now, the advantage of proceeding like that is, whereas the periodic table is finite and chemistry can be sometimes quite difficult to persuade to yield the right materials you want, the structures you can imagine are almost infinite in number. And so with these metamaterials we can achieve properties which were not accessible to us before. And so it's really opened up a whole new world in optics and electromagnetics. So these structures were first engineered for not optical waves but for radar waves, because it's much easier there. The radar waves are typically 10 centimeters in wavelength, and therefore this requirement that these structures are less than the wavelength is much less severe. So here's one of the first metamaterials made by Mike Wiltshire when he was at Marconi, and it just consists of little copper rings etched on a circuit board, and the dimensions here are about 5 millimeters, comfortably less than the wavelength he was using to look at them. So that was one of the first metamaterials, and that idea rather took fire, and the first people to be interested in that were David Smith and Shelley Schultz, who were then at University of California, San Diego. And they took these little rings, which, by the way, they have a ring-like shape, so when you put a magnetic field through them, that, according to Faraday, induces a current round the ring, and the current in turn produces another component of the magnetic field. So these little rings have a magnetic response, a totally artificial magnetic response, because they're made of copper, which isn't a naturally magnetic material, but it can be made to appear so by altering its shape. So this has a magnetic response, and whenever you see a thin wire there, it's a bit hard to see because it's actually on the other side of the circuit board. It appears as a shadow. And this straight wire responds to the electrical fields, not the magnetic fields. And so this structure has a magnetic and electrical response. And the way David has made it, it's actually a material in which the electric and magnetic response is in the opposite direction to the applied field. And it turns out that, and if I have time, I'll come to this later, this actually creates negative refraction. But that's not what I want to talk about for the moment. So these metamaterials, sometimes you can create negative refraction, but also you can create any range of properties you want. Now, a cloak doesn't require negative refraction, but it does require a rather complex grading of the refractive index. And David Smith achieved that by altering the shape of these little metamaterial structures as his cloak, which you can see here, grades from the inside to the outside. And here's the refractive index profile. So what we have here is a cylindrical cloak. It's going to be a cloak against radar waves. It's an experimental thing, so it doesn't look anything like Harry Potter might wear. It's between two heavy aluminium plates, and you send in a radar wave, and the idea is to hide what's in this inner cylinder here. The radar waves never get in there, and they're steered around this structure here by the variation of the refractive index. This is a more detailed picture of what's going on in David's structure. These are the little split rings, we call them. They split with a gap here, but the current flows round and gives you the magnetic response, and these are the parameters he changed to alter its properties. Here's a picture of the experiment, two heavy aluminium plates, the radar waves go in between. This is all absorbing material so that you don't get any stray reflections. And here's the cloaking structure in the middle. Cloaking structure is green, and the hidden bit is inside. And on top he pokes through a probe which you can measure the magnetic field with. So that was the first cloak that David built. And we built it in a great hurry because we didn't want to be scooped or anything. We'd already published the theory, so and here are some results. It's a bit complicated, so let me try and explain this. This is the cloak. This is the region you're cloaking, and you want the rays to go through. These are rays of radar waves, not light, radar waves, and you want the rays to go through so that they avoid this region here, but carry on in the same straight line as they do before. So this is a computer simulation of our ideally recommended material properties. So this is the ideal. The waves come through, they're very distorted here, and then they come through the other side completely unaltered in this region here. So anybody sitting here would see what's behind the cloak. They wouldn't see the cloak. They would certainly not see the contents of the cloak. Here is a computer simulation with instead of the ideal properties, the experimental properties which we think we can realize for the cloak. And you see the rays get bashed up a little bit, but the cloak transmits the waves. If these waveforms are straight, then you can see an undistorted image on the far side. They're a little weaker, so instead of a completely transparent cloak, what you'd see is a little grey patch in the sky, okay? And here's the experiment. And the experiment is pretty close to the simulation, and it demonstrates the principle that you can indeed guide waves around an object and leave it hidden. This is what would happen that if you didn't have a cloak here, so this thing is completely stopping the rays getting through, there's a shadow here, and you're messing everything up big time. And when that was published, I was giving a lecture that morning in Rochester, and people were waving pieces of paper at me in the audience, and I thought, I didn't know I had so many friends, but it turns out what they were waving was a copy of the New York Times. And the New York Times was so excited about the cloak that they put it on the first page of the Science Times, which I was rather amused by at the time. So that was the demonstration of the cloak. It was for radar waves, it was two-dimensional, so on and so forth. And what people are doing now is trying to make a real optical cloak instead of using radar waves where all the structures are rather big and the engineering is easy. They want to move up to higher frequencies, to shorter wavelengths. The engineering to make these metamaterials becomes very hard, but possible. And to help them, one of my postdocs, Jensen Lee, designed a new sort of cloak, which is what we call the carpet cloak, for reasons which will become apparent in a moment. The way this cloak hides something, it acts like a lens. Now, most lenses you want to magnify something, okay? But if you have a lens that makes something seem very small, and if you have a lens that makes something so small that you can't see it, then that lens is cloaking something. So a cloak is really a lens that makes the object inside the lens appear very, very small. Now, there are actually three ways you can make something very small. You can crush an object to a point, and points are invisible. You can crush an object to a very, very thin wire. You can't see very thin wires either. A hair is very hard to see. Or you can crush it to a very flat sheet. Now, you can certainly see a very flat sheet. It reflects. And in fact, the result of that squashing means it reflects. It's very, very reflecting. However, there is a way of hiding a mirror. If you put a mirror on top of another mirror, you just get one mirror. And so the second mirror you can't see because it's doing exactly the same thing as the mirror underneath it. So you can hide a mirror on a mirror. And this is why we call this a carpet cloak, because the idea is to have a base of a mirror, and what you want to do is to have a tunnel here in which you're going to hide stuff. And we want this tunnel to be squashed down so that it actually appears, instead of being curved, flat. So we're going to use this transformation optics to, if you like, we're going to create this tunnel by pulling it up from a flat sheet, and then we compress space, and this is the refractive index which the compressed space implies. And light is going to be guided around this bump here. And it turns out that as you progress from the dimensionality of a point to a line to a flat thing, the cloak gets easier to build. And this cloak is very easy to build, and I'm going to show you some experiments in which the cloak is built. So the signature of a little tunnel, which is highly reflecting, is that if you bounce light off it, instead of getting a single reflective beam like you do from a mirror, you get 2 or 3 beams from the facets of the tunnel. So if I was scanning the laser beam over the surface, you'd suddenly see a twinkle as 2 beams appeared instead of 1 from this region here. It will be very easily seen. But if you wrap the cloak around it, as we see in this computer simulation, the beam returns only a single reflection rather than the 2 which you see here. And that's the test of whether you made a good cloak. Do you see 1 beam or 2? And this is the realization of an optical cloak made by the Tsang group at the University of California, Berkeley. It's manufactured in silicon and silicon oxide, and the variation in the refractive index is made in a very simple way. You just drill holes in the silicon and make it less dense, and we know how to do that. It's very expensive machinery, but you can do it. So here's the cloak, here's the bit you're going to hide, and the whole dimension of this, well, it's not really Harry Potter, but it is a few microns across. And so the cloak's going to be transformed into a virtually flat object. Here's an electron micrograph of the realization of that. This is the silicon with the holes drilled in it by a focused ion beam. And here are the dimensions 1 micron, so this is about 10 or 20 microns across, and the cloaked region is 2 or 3 microns across. And here are the experiments in which you see the single reflective beam from the mirror surface. You put a bump in that surface and you get multiple reflections from the facets on the cloak, and that's seen in the experiment here. And then you put the cloak in place, and instead of the multiple reflections, even though you've still got the tunnel there, you get a single reflection again. So you really have made that thing stealthy. So as I explained, our original idea for reason for developing the cloak was as a demonstrator. In a sense, it was a joke that we had these ideas that we wanted to smack people in the face with and say, hey, pay attention, this is important. And it certainly achieved that. There was a great deal of fuss, more thanks to Harry Potter than to our equations, I think. But there's a lot more to transformation optics than a cloak. And I want to spend my last few minutes talking to you about those other things. Now, I did allude earlier to a phenomenon called negative refraction. Now, the key name here is a man called Veselago. And what Veselago said is that this is just to remind you of the transformation optics. So I need the next slide. What Veselago said is that if you take Snell's law, which is this thing here, and the refractive index is defined by these 2 angles here, then it's possible, in theory, to have a structure in which instead of the light going this side of the normal, as it would in water or glass, in Veselago's structure it will go this side, and this makes this angle negative relative to this one here. And if you go back to Snell and ask what the refractive index is, then that has to be a negative number. Now, you might say, oh, these mathematicians, they get excited about everything. They turn about complex numbers next. So why is it, how can I explain to you that a negative refractive index is interesting and important? And I go back to this idea that Einstein taught us, that a distortion of space is like a change in the refractive index. So I can imagine that if I squash space a little bit, then the refractive index will increase, and okay, the light goes in a wiggly line, deviated a little bit round the sun, whatever. If I squash space a lot, then it's deviated some more. And suppose I really, really squash space. Here's a bit of space, okay. I'm not Japanese, so I'm not very good at origami. And I'm going to squash this piece of space. I'm going to squash it till it's infinitely squashed, and there's a singularity at that point, and the singularity in mathematics says, hey, sit up, take notice, something's about to happen. And the thing that happens as you push harder is that you actually fold space back on itself. So instead of having an ordinary space which, as we mathematicians say, is singly connected, you have a space which at one point you have 3 bits of space to contend with at the same time. And that is really weird. What does it mean in terms of physics and what we might see? And Veselago explained that to us. So here's a piece of space, and I've inserted a piece of material with negative refractive index here. Now, I can look at that in 2 ways. I can look at it as Veselago said and said, well, you have a negative angle of refraction here. This steers the light back to the axis. So if I have a focus here, if I'm looking at an object here, then the same object will appear here and here again. So you actually get 3 foci. But this space wave tells you that what the light thinks it's doing is it goes along and says, yes, there's something here, and oh yes, I've got to go back, and hello again, I've seen the object a second time, oh, you want me to turn around again, and I see the object a third time. So the light actually sees that object 3 times. Now, this, therefore, explains Veselago's lens. This is a lens, of course. It focuses light and makes an image. What wasn't realized at the time when it was first proposed is it's a very unusual sort of lens. Now, this refraction way of looking at it just treats it like an ordinary lens in which you have rays of light. You don't bother about the electric and magnetic components, and therefore you might expect that just like any other lens, its resolution will be limited by the wavelength. You're not looking inside the wavelength. But this transformation optics theory, which talks in terms of distorting space and refractive index being equivalent to a distortion of space, that is a theory not at the level of the ray approximation, but it's at the level of Maxwell's equations, which, at least in classical physics, are a complete description of how light behaves. And so, if this description is complete and looks inside the wavelength of the component, fields and so on and so forth, then the prediction is that this focus is rather unusual. It's not limited by the wavelength. It can be perfect, but you have to make the lens precisely as Veselago said you should. And if you do that, then resolution will be perfect. Now, experiments have been done in which approximations, again, you can never make anything completely perfect, but this theory says that the old theory said that a lens is limited by the wavelength, so don't even try to make it better than the wavelength. What the new theory says is, no, that's not right. You can, in principle, do the better than the wavelength, so please try. And people are trying very hard, and so far they've got resolution of something like a 20th of the wavelength, and they're going on and trying to do better, which involves better techniques and better materials, of course. Now, I would like to show you these experiments, but since I'm a theorist, I want to show you some more theory. So, once you've got over the excitement of this lens being perfect, and handle all the people who said you're an idiot because it isn't perfect, then you realize that, in fact, it's perhaps a little boring, because being perfect, it's a perfect copy of the object here in the image. It's exactly the same size, but what you usually want to do with a lens is to make something bigger or smaller. Well, I take you back to this concept of distortion of space. So you want something bigger, okay, let's stretch it, let's change the coordinate system. So what I'm going to do, I'm going to take this Vestilago lens and I'm going to bend it round and I'm going to make a spherical shell out of it. And as I do that, I distort the shape of the object and the image. The image may become bigger depending on which way I fold the lens. Let's suppose the image becomes bigger and the object is inside the shell and is smaller. So I can do that. Of course, when I bend the space, I have to change the optical parameters. For the cognoscenti, here are what the optical parameters are, but never mind. What they consist of is a bit of negatively refracting material here, and what this lens does, which we made from the original Vestilago lens, is to take everything that's inside this green shell, and if you look at this thing from outside, what you see is a much bigger representation of this red shell here. So everything inside the green shell is magnified and appears inside the red shell here, which, by the way, is bigger than the lens itself. So that's rather interesting because if you can trust the theorist to do an experiment, I don't know if you've ever noticed a very curious thing about a glass of water. It is that you can't see the glass. The water goes right to the edge of the glass. See that? Try it at home. And the reason is very simple, actually. It's just that any ray of light which strikes the glass is always directed into the water, and therefore it looks as though the water is as big as the glass. In effect, the curved glass is acting like a magnifying glass of just the right strength to make the water as big as the glass. So what is this lens doing? So we put some water in the red region in the middle. Instead of glass, we have some negatively refracting substance here. And now, the water appears out here. The water is now bigger than the glass. And figure out how that can happen. It's really weird, but it can, and it does. So here's a computer simulation. Water has its uses. Of some light going through this lens here. So the light appears unaffected inside this red sphere. As soon as it hits the blue sphere, it starts being scattered in a really weird way. And I think you can see that the contents of the green sphere are just a compressed version of what's in the red sphere here. So here the lens is acting the other way. Instead of making small things big, it's making big things small. Reciprocity, that does that. So it really does what I say. And those of you who know about ray tracing may ask how these rays here, which don't actually touch the lens, nevertheless are gathered by the lens and put inside this inner region here. I'll leave that as a paradox for you. What else can we do with this lens? Well, it makes big things, small things, big. And it doesn't really matter how small they are or how big you want them to be. At least in theory, it doesn't. So one thing you can do is, there are many things in optics which only work if they're really big. And one of the things is the shadow. So if I take a black object, if it's big, it has a shadow, of course. But if it's really small, of the order of the wavelength or less, then diffraction effects take over and they fill in the shadow, and a small object doesn't have a shadow. It scatters the light all over the place, but there's no sharp shadow. So if you want to make a really small parasol, what you do is to say, well, okay, as a small parasol, I'll pop it inside here, and then it will appear like a big parasol and create a big shadow, bigger than the parasol and bigger than the object which is magnifying it. And that's what my student Wei-Chung Wei has done here. So here's a computer simulation. Inside he's got a black object. He's surrounded it by this curved Veselago lens, and it's creating this is all vacuum out here, and it's creating a shadow which is much bigger than any of the objects which are responsible for it. There are many other tricks you can play with it, but I think you can see that we're actually having a lot of fun with these new ideas in optics, and I hope I've conveyed to you that sense of wonder which we're all feeling at the moment. Thank you.